And a reminder, one more week of work and you get a long, right, much deserved break. Right? An entire week off. Okay. All right. So here this is titled section 2.9, building a function from words. Okay. We're basically solving word problems. And with me, there are 4 basic steps in solving a word problem that I use. The first one is draw a good picture. Math is very visual oriented, okay? And so drawing a good picture, right, goes a long ways to helping to solve the problem. Okay. Second step, define your variables. Right? What's X represent? What does Y represent? What does Z represent? Right? And so forth. Okay. 3, set up the equation. Right? And the equation is just a mathematical model, right? Describing what it is we're trying to solve. Okay. And then step number 4, solve the equation. Okay. Now in the examples we're going to be working, we're going to be putting the emphasis on the first 3, not so much on the 4th one. Okay, step 4. And the reason for that is a lot of times, right, the math we need to solve the equation is calculus. You haven't had that yet. Okay? So we're like doing the algebra for the calculus, step 4, okay, in these problems. So in example 1, we're given a rectangle has area 16 meters squared. Express the perimeter of the rectangle as a function of length of one of its sides. So, step number 1, draw a good picture. So here's our rectangle. And it has an area of 16 meters squared, right? So area is equal to 16 meters squared. Okay. Express the perimeter of the rectangle as a function of length of one of its sides. So you know the perimeter is the distance around the outside of the rectangle. Okay. It's the sum of the lengths of the 4 sides. Okay. So let's define our variables. Okay. Let's let x be the length of these 2 sides, and let y be the length of these 2 sides. So x is equal to width, and y is equal to length. Now you can also define them as width times, x could be height, and y is width. Right? But I'm doing width and length. Okay, x is the width of the rectangle, y is the length of the rectangle. Okay. Now, we know that the area of a rectangle is width times length. Well, the width in this case is defined by the variable x, and the length in this case is defined by the variable y, and that area, x times y, or width times length, is equal to 16 meters squared. So the way I've defined x and y, right, x times y is equal to 16. Well, we can express y, the length, as a function of the width x, right? We divide both sides by x, and we get the length y is equal to the area 16 divided by the length x. That's important. Because remember, we're going to write the perimeter as a function of one of the variables, not both of the variables. Okay. And so the perimeter P, so that maybe let's just remind ourselves what perimeter is, right? Perimeter is the total length of the four sides. So the perimeter P is equal to x plus y plus x plus y, right? Well, that on the right-hand side, combining like terms, we get the perimeter P is equal to 2x plus 2y, right? So we have the perimeter expressed as a function of two variables, x and y. But we know from our area constraint, the area is fixed at 16 meters squared. So we know from our area constraint that the length y is equal to 16 divided by x. So we replace y over here with 16 divided by x. And we have the perimeter as a function of one variable instead of two. So the perimeter P can be written as 2x plus 2 times 16 over x, right? Whatever x is, y has to equal 16 divided by x. Okay? Whatever the width is, the length has to be 16 divided by the width. Okay? And when you simplify, you get the perimeter is equal to 2x plus 32 divided by x. So whatever the width x is, the perimeter is equal to 2x plus 32 over x. Okay. And that's because the area of the rectangle is fixed at 16 meters squared. Okay. All right, that's A. B is, what is the domain of this function? Well, can the width x be negative? No, it's always positive, right? Can it be 0? I never saw a rectangle with 0 width, right? It has to be positive, number greater than 0, right? So the domain is that x, the width, has to be greater than 0. It can be as big as you want it to be, okay? And then the larger the width is, the shorter the length is. Okay? If x is, what are we giving it in meters? If x is 1 million meters, if the width is 1 million meters, then the length is 16 divided by 1 million. Okay. So it can be as big, right, as you want it to be, and the bigger x is, the shorter y is. Okay. Are you with me? And then it's that way so that the area stays fixed at 16 meters squared, regardless of what the how big or how small the width is. And so in interval notation, the domain is 0 to infinity. Because the area is fixed at 16 meters squared, no matter how big the width is, we can make the corresponding length shorter. And no matter how short the width is, we can make the length longer. So that x times y is equal to 16. Okay. Any questions? Alright, let's take a look at example 2. It's a similar setup, a rectangle. Now you're given the perimeter of a rectangle instead of its area. A rectangle has a perimeter of 20 meters. Express the area of the rectangle as a function of the length of one of its sides. So we're going to go from expressing the perimeter as a function of the length of one of its sides to the area as a function of the length of one of its sides. So this area is no longer fixed at 16 meters squared. The perimeter, the distance around the rectangle, is fixed at 20 meters. Okay. So x is width, y is length, and we know from the previous problem the distance around the rectangle is 2 times the width plus 2 times the length. Okay. We're given that the perimeter is fixed at 20 meters. Okay. So the perimeter 20 is equal to 2 times the width plus 2 times the length. And when you simplify this, right, you can divide both sides by 2, and you get 10 on the left is equal to x plus y on the right. Okay. So the width of one side plus the length of one side is equal to 10 meters. Okay. Well, we can express the length as a function of the width, right? We subtract the x from both sides, switch the 2 sides of the equation, and we get the length y is equal to 10 meters minus the width of one side x. So y is expressed as a function of x. Okay. Well, we're told to express the area of the rectangle as a function of the length of one of its sides. So we can write the area as a function of x. Area of the rectangle is width times length. The width is x meters. The length is y meters. And now I can replace y on the right hand side with 10 minus x, and I have the area as a function of x only. So we can replace the word area, right, with f of x. Area is a function of x, and it's equal to x times 10 minus x, right? Y is equal to 10 minus x. So that's the area of the rectangle as a function of the width, x. Okay. Now for this problem, we got to state the domain. Well, you know area has to be positive, right? Can't be negative. So this is actually a quadratic on the right, quadratic function. You distribute the x, and you have 10 times x minus x squared. Okay. For what values of x is the quadratic function positive? Okay. Well, one thing, right, the width can't be negative, right? So x can't be less than 0, and it can't be equal to 0, but it has to be greater than 0. So x has to be greater than 0, the width. But in this term right here, there's a limit to how wide the rectangle can be. If the width is 11, we have 10 minus 11, which is -1, and -1 times 11 is -11, and now we get negative area. Okay. So the only way the area can be positive is if x is less than 10. If x is greater than 10, right, the area is negative, and if x is equal to 10, right, the area is 0. So the width has to be greater than 0 and less than 10. Okay. If x is less than 0 or greater than 10, the area is negative. Okay. So combining these two inequalities, we get the combined inequality that x has to be greater than 0 and less than 10, which in interval notation is parentheses 0, 10, right parentheses. That's the domain. Any questions? Okay. So let's take a look at example number 3. An open box is to be made from rectangular piece of cardboard 10 feet by 4 feet, cutting squares a side length x feet from each corner, folding up the sides. Find an expression for the volume of the box as a function of the size x cut out at each corner. So again, this is where a good picture is worth 1,000 words, and it can make solving this type of problem a whole lot easier. So we have a rectangular piece of cardboard. And from this rectangular piece of cardboard, we're going to cut out a square in each corner. Of width x. Okay, that's supposed to be a square in each corner. Okay. So we got a flat piece of cardboard. We're going to cut out a square from each corner, and then we're going to fold up the sides and create a box with no top on it. Right? This box does not have a top. Right? That's what it means by an open box. Okay. So the original piece of cardboard is 10 feet long and 4 feet wide. Now we're going to cut a square of equal size from each of the 4 corners. You know, square, all 4 sides of square have the same length, and so we'll call that length x. Now this is where you got to visualize. Okay, visualize this piece of cardboard now is missing the 4 corners, right? And now we're going to fold each of these 4 sides up, right? So from here to here is going to be one side of the cardboard box. From here to here is going to be another side, right? So this flap here, this is going to be like a flap that gets folded up. This is like a flap that gets folded up. This is like a flap down here that gets folded up. This is a flap here that gets folded up. Those 4 flaps get folded up, and now we have a box with no top on it. Okay. Well, the total length of the original piece of cardboard is 10 feet. So when we cut out this corner x by x and this corner x by x, the length of the bottom of the box is going to be 10 minus x minus x. Which is 10 minus 2x. Okay. And when we cut out the four corners, right, the length of this flap right here is going to be the original 4 feet minus x minus x from cutting out the two corners. So the width is going to be 4 minus x minus x. 4 feet minus x minus x. So that is the width of this side, the width of this side, and then the length of this side is also 10 minus 2x. Okay. So this is the base or the bottom of the box. Okay? This rectangle inside here is the bottom of the box. Okay? After we cut out the four corners and fold up the flaps, take them together, take the flaps together. Okay? Well, these flaps, their width of each of these flaps is x feet. So when we fold up the flap, the height of the box is equal to the width of the flap, which is x feet. Okay. So the volume of the box is going to be, right, the area of the bottom times the height of the box, which is the width of the flaps. Okay. So the volume of the box is going to be the width times its length times its height. So maybe I'll write it this way. Volume is equal to width times length. You know width times length is area, but width times length times height is volume. Okay. So width times length is area, but width times length times height is volume. Okay. And so the width of the box, right, the bottom of the box is 4 minus 2x. The length of the bottom of the box is 10 minus 2x. And the height of the box is the width of each of these flaps, x feet. So we have volume is equal to width, which is 4 minus 2x, times length, which is 10 minus 2x, times height, which is the width of the flaps, which is x. And we're done. We have found an expression for the volume of the box as a function of the size x cut out at each corner. We cut out a square x by x at each corner to build this box. I mean, this is a real manufacturing problem. Okay? Yes, ma'am.
We don't need to simplify that.
No. Just said find an expression. Okay. If you simplified it, it would be a polynomial, right? You remember what degree that polynomial would be? We're going to be studying that next. Okay? That's a third degree polynomial. All right. Key questions. Okay. All right, let's take a look at example 4. rectangle is inscribed in the parabola y equals 5 minus x squared with the base on the x-axis. Write the area A of the rectangle as a function of x. I wish they hadn't put this shaded area inside there, but they did. So let me see if I can reproduce this on the board here. So you know a parabola is, this parabola is symmetric to the y-axis, right? The right half of the parabola to the right of the y-axis is a mirror image of the parabola to the left of the y-axis. It's the best I can do, okay? And so this is a graph of y equals 5 minus x squared. And right, exam 2, right, you know how to find the x-intercepts. Set y equals 0 and solve for x. And you get x is equal to minus the square root of 5 and x is equal to plus the square root of 5 are the two x-intercepts. Okay. So this is square root of 5 here. And this is minus square root of 5 over here. Now, inside this parabola, with the base of the rectangle on the x-axis, we inscribe a rectangle. Right. Inside this parabola, we inscribe a rectangle with its bottom side on the x-axis. Okay. What is the area of that rectangle? Okay, as a function of x. We can do that. Well, here's the origin. Okay. So let's call the distance from the origin to the right edge of the rectangle x. The distance from the origin to the right edge of the rectangle x. Okay. This is x on the horizontal axis. Then due to symmetry, the left edge of the rectangle, okay, is at minus x on the horizontal axis. Okay. So the distance from the origin to the right edge is x units, and the distance from the left edge to the origin is also x units. Okay. It's labeled x and minus x on the horizontal axis. So this total distance, this total length of the rectangle is x plus x or 2 times x. Because of symmetry, if the length of the bottom of the rectangle from the origin to here is x units, then the length of the bottom of the rectangle from here to the origin is also x units. And so the total length of the rectangle is x plus x units, which is 2x units. The height of the rectangle is equal to the value of the function at that value of x. So the height of the rectangle is equal to the value of the function at this value of x, which is given by 5 minus x squared, right? That's the equation of that parabola. So we know what length times height is now in terms of x. So the area of the rectangle Well, the width of the rectangle is 2x units, right? Again, if the distance from this point on the bottom of the rectangle to the right edge is x units, then it's also x units from the left edge of the rectangle to the origin. And x plus x is equal to 2x. So the total length of the rectangle, or total width of the rectangle, is 2 times x, and the height of the rectangle is given by the value of the function right here. The height of the rectangle is equal to the value of the parabola, the quadratic function at this point right here. And that's equal to 5 minus x squared. So the area is the total width times the height. The height is y, okay? And y is equal to 5 minus x squared. And so we can write the area as a function of x. So I'm going to use a of x. Area as a function of x is equal to 2x times y, which is equal to 5 minus x squared. So this is width times height. The width of the rectangle is 2 times x, and the height of the rectangle is equal to the value of the quadratic function at that value of x, which is 5 minus x squared. Okay. Then again, to find the optimal size of the rectangle, we'd have to use calculus. That's math 120 material. Okay. All right. So we'll pause right here, and we'll wrap this section up first thing tomorrow. Okay.